Hey guys, welcome to the class. Another video. I hope you remember that in the last session we were talking about the valence bond theory and how it is used to solve the molecular geometry, and also the concept of hybrid orbitals, where the orbitals which are involved in the bonding come together and play as a single type of orbital. So we were talking about examples, and we were about to take the example of BF3. So boron is 1s2, 2s2, 2p1. Now obviously this is sort of, if s loses one electron, it would be more stable, right? So it becomes, the s becomes promoted to 2s1, 2p2. Now F3, that means we have 3 orbitals which are going to be involved. So this becomes hybridized, right? This becomes hybridized to sp2 orbitals. So we have 3 sp2 orbitals which are going to participate in the bonding, whereas this p is going to just remain there, right? Now again, how does an sp2 orbital looks like? So somewhat you can assume it to be a little bit towards 1. So it would be like they are the corners of there are 3 corners of an equilateral triangle, right? So they will occupy the 3 corners. This is not the exact place. I would like them to draw. Yep. So they would occupy the 3 corners of the equilateral triangle, and remember, they would not be symmetrical, because the symmetry is a pure one of the example of the pure orbital. Now let us bring chlorine orbitals. Now these would be perfectly symmetrical, right, like this. Although my drawing is not very perfect, but this is the chlorine and this is where you have your electrons, right. So this is how you describe the hybridization of BF3. Now let us go ahead. So here the central atom, as you can clearly see, is oxygen. Oxygen is 8. That gives you 1s2, 2s2, 2p4, right. So we can clearly see that we have 2s completely filled and p here filled, right. So that sounds okay, but that also brings us to the next thing, that we have 2 lone pairs. Now this is how this H2O is different from the past examples that we have solved, that H2O has got 2 lone pairs, right. So what are the orbitals that are going to be involved here? S and 3 p's, right. So this is clearly a case of sp3 hybridization, right. So these orbitals become as 4 sp3 orbitals. Now in the 4 sp3 orbitals, 2 are going to hold the lone pair, whereas the remaining 2 are going to hold the bonds, right. Now I hope you remember the VSEPR discussion of the water molecule, and if you do, you would remember that oxygen would be not 109 degree. Remember, since there are 4 electron pairs, this is going to be a tetragonal electronic geometry, but because we have 2 lone pairs, this comes out to be 104 point something because of the lone pair of electrons, right. So how does an sp3 orbital look like? So sp3 orbital, they look like they occupy the corners of a tetrahedron, right. Now let us try to figure out the last problem, that is XeF4. But guys, I already have included more problems if you want to solve them. Now I hope you remember that because we have 6 electron groups, so this is going to be all octahedral when we talk about the electronic geometry. Now, if we talk about the molecular geometry, because we have two, so you also know that this is going to be square planar. Why? Because of the lone pair electron groups that are above and below. Now, what we have to do is we have to figure out the hybridization, right? That is all this video is all about, figuring out the hybridization. So, XeF4 means you need 4 bonds. Now, P6, that's not going to be easy for us, right? Because we need 4, right? So, let's first write 5s, then let's write 5p. Now, definitely we need some promotion here first of all. So, let's promote them. So, I am going to promote them into D, right. So, this is the same 5s, 5p and now 5d. Now, 5d, remember 10, right, they have 10. So, we need to promote. So, let's erase 1 electron from here, right. That means now you have 4 orbitals which can take the bonds, right. But we have now 2 lone pairs, right. So, if you see the number of orbitals that are being involved here, that is s, p3 because this is carrying the lone pair, and d2. So, all you have to do is you have to consider the orbitals that are going to be involved either in bonding or carrying the lone pair on the central atom, because the lone pairs do influence the geometry. So, you will have sp3d2 hybrid orbitals, and how many? 1, 2, 3, 4, 5, 6, 6 such orbitals, right. So, this actually works in our favor, in exactly what we want, like. So, we have F, 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 right, and then do we have the lone pair above and below, right. So, remember that this is the video where we will be talking, we have been talking about the valence bond theory. Until now, we have been avoiding a certain type of molecules, 2 specific types where we have more than 1 central atoms, and even though we were talking about compounds where we did have double bonds, like SO2, we did talk about SO2, they have double bonds. We have not talked about the geometry of double and triple bonds, right. Now, this specifically the central atoms is very easy. Fairly, I hope you remember the steps, right. Write the Lewis formula, count the central and bonded and lone pair of electrons, arrange according to VSEPR, and then the bonded and lone pair electrons. And now that we have one more step, that is determine the hybrid orbitals. In case of central atoms, we will just carry the steps for all the central atoms. So, it is fairly easy, but the geometry involving double and triple bonds is something to be understood. So, rather than including them in this video, I am going to bring a next one where I will be dealing with these 2 topics in detail. I hope this makes sense.